talk now, right? Okay, good morning everyone. Welcome to the last session of this tutorial. So here in this session, I'll cover the MAERI, which is an open source framework for generating the DNN accelerator that supports a variety of the data flows. So before I begin my session, so I'd like to acknowledge these people. So from BlueSpec, Mr. Charlie Hawk and Vishur Nikhil. So thank you for providing VSV license. And from GT, so Anand Samazar and Eric Chin and Yoshua Emmanuel, they helped. So actually, Anand is the co-author of the MAERI paper, and other people helped to synthesize the module. So this is the outline of my session. So the tool flow MAERI, and I'll discuss design and architecture, and I'll show you the source code structure and how to use MAERI frontend, and I'll do one demo, and we'll proceed to the hands-on exercises. So let's begin with tool flow. So as Tushar introduced, MAERI receives two inputs. So first one is the hardware resource description, the number of PEs and distributions and reduction bandwidth. And the layer descriptions, which means the layer dimensions for each variable, like Maestro. And we have MAERI frontend, and we have building blocks library implemented with BlueSpec system Verilog. And we go through the VSV compiler, and we can generate either the Verilog file or cycle accurate simulation.
So I just wanted to add one point. So the layer description is just used for the cycle accurate simulation. So right. The Verilog files are just generated by the resource description. So it's not a specialized design for like a layer. I mean, it's basically a general architecture and accelerator.
Exactly. Thank you. And because we implemented the MAERI using BlueSpec system Verilog, so I'd like to briefly talk about what is the BlueSpec system Verilog and what's the feature of it. So it's basically a high-level hardware description language that generates the fully synthesizable Verilog. And it is originally based on Haskell and currently following the system Verilog style more. And it contains some strong type checking and polymorphism and some intuitive model interfaces. And it has something called guarded atomic action model, which provides a coarse-grained description of parallel behaviors in the hardware, which makes the debugging and development of the hardware much easier. So if you want some details, then please refer to this literature. And let me discuss the design of the MAERI. So before I begin, so let's talk about the convolutional layer again. So the left side is the typical diagram we use when you describe the convolutional neural network, which is based on the sliding window scheme. But it is also, we can also describe it as the neuron diagram like this. And if we take a look, the sliding the wait window over into input activation is the same as sliding over the output neurons in neuron diagram. And for each output neuron, what happens inside it? So it has multiple pairs of input and weights and generates one output. So within this neuron, we perform the weighted sum computation. So which consists of the independent multiplication of each input and weight pair and accumulation of the multiplication results. So if we want to get a fully flexible accelerator that supports variety of the data flow we've seen in previous session, so we might want to get an illusion like this. So the multipliers and adders are compute units in the DNN accelerators, and we might want to make it as some kind of pool so that we can grab any number of compute units, so such as multi-log and add-log, like we use malloc in software. So we want to realize this kind of illusion. So using this kind of the allocation, so we can construct some structure like called virtual neuron, which is the temporary grouping of computing units for an output neuron. So with this illusion, we can construct multiple of the virtual neurons and do the computation. But how do we enable this kind of flexible grouping? So to realize this kind of illusion, we need to provide flexible connectivity among all of the compute units, including the adders and multipliers, and also between the compute unit and buffer. So we might think of implementing the all-to-all connection of all of these compute units and buffer, but that is not practical because it requires a lot of wires. So more practical approach is minimal switches augmented to each compute unit. So for multipliers, we allocate one port for the distribution of data from buffers to the multiplier, and one port for local forwarding between multipliers. And for adders, we allocate 2 ports for the collection, which is the reduction, and we allocate extra port for flexible mapping. So I'll come to the details about it. So now the question is this: using these minimal switches, how do you design a spatialized connectivity allowing all kinds of the flexible mapping? So to do that, let's first take a look at the distribution, which is the data transfer from the buffer to each multipliers. So we in MAERI implemented a fat tree-based structure, which has extra bandwidth near the top. So it can transfer multiple data at the same time, which provides high bandwidth. So as I mentioned, it is fat tree-based topology. So it does support multicasting because it is tree-based structure. And because of the extra bandwidth near the top, we can send multiple multicasting at the same time. And for local communication, which is the data we use among multiplier switches. So like other accelerators, we implement the local connection between the multipliers. It enables spatial temporal data reuse. So because we are sending data from one multiplier to another multiplier, it is spatial reuse, but it is done through the time window, so it is spatial temporal reuse. And for reduction or collection of outputs, we implemented some structure like this. So as you can see, this is also tree-based, but unlike binary adder tree, we have extra link around here. So to define the extra link formally, so the extra links are between the adders who don't share the same parent at the same level. So how does it work? Let's take a look at an example. So we want to construct virtual neurons like this. So each box means a separate virtual neuron, and we want to send data. We want to reduce data at the same time. So if we use this structure, we can reduce data in this manner. So as you might notice, the red virtual neuron uses this link to perform the reduction at the same time. So the red link enabled the simultaneous reduction and also the extra bandwidth near the top of this reduction tree. So 2 factors enable the simultaneous reduction of some arbitrary shape of virtual neurons. Sure.
So in this example, can you back one slide where the blue and the red bubbles collapse?
This one?
Yeah.
Yep.
So the last operand of the blue set and the first one of the red set, they go to the same address.
Yep.
And you don't do the actual addition. Is that
right? Right. So this adder is not 2-input adder, so it is basically a 3-input adder. And
but you don't want the red and the blue
right.
data
Yes, exactly. That's why we need extra bandwidth. So when we have the output, then we don't go through the adder, but just forward it to the next level. Yeah. So as you could observe, so this extra link enabled the red virtual neuron to operate at the same time. So we named this structure as augmented reduction tree. So the features of this structure is it has extra link. So thanks to this extra link, which is the red link in the previous example, it supports non-blocking in-network reductions of arbitrary virtual neuron sizes. And that eventually provides high compute utilization by minimizing the stall of the reduction. And this structure has extra bandwidth near the root switch, so it enables multiple reduction simultaneously. So let's take a look at the architecture. So how to implement switch microarchitecture? So for multiplier side, it is nothing but multiplier and 2x2 switch, which is pretty simple. So 2 muxes and small 5 volts. And for adders, so because we need to support the 3-input addition in some certain cases, we have adder and 3x2 switch. And please note that we also have the comparator. We might include the comparator inside this adder switch to support the pooling layer. Yeah, because the pooling is also the inherently reducing some information or summarization of information.
And you can also use that for ReLU.
ReLU. Let me see. I think for yeah, right. That's a good point. Yeah.
At the root, you mean, right?
You would have to send in 0 as an extra.
Yeah, right. That's a good point. Yeah. Okay. So as you can observe, so it consists of several muxes and the compute unit, which also exists in other accelerators, and some 5 volts. So it is lightweighted structure. Sure.
I think maybe also barriers, because you have data dependency with your operations.
Sorry, I don't.
Don't you need barriers? Yes.
Barriers. So see, is it related to the latency insensitive channel? So each switch doesn't operate until it receives 2 operands, and if it has only 1 operand, it waits until it receives another operand to the other side. So that is kind of some kind of implicit synchronization.
What happens if the output FIFO is full?
Then it stalls the execution, even if they have 2 inputs, because output is full. So kind of back pressure. So if the buffer at the output is not available, then it let the switches know that about the buffer status, so the switch doesn't generate new output.
I think this is a great question, and it's one of the biggest differences between ISCs and sort of the GPU model, is that you can do precise synchronization. That is to say that you only synchronize on the things that you need. You don't. If you're doing a tile of size 1,000 and number 5 gets stalled, it doesn't stall number 6 or 7. Whereas even in the GPU model, you have to do a barrier and say everybody reaches the barrier. So here it's just.
No, here you need only on the adders, right? The multipliers are done independently. But again, on the adders, how do you? Is it hardware managed the synchronization?
Yeah.
Because I can't see it in the model.
It's hardware managed Q back pressure.
Right.
Yeah.
Yeah. That's a great question, and yeah, great point. Thank you.
Yeah, I guess we do have barriers between layers. Like there's the
between layers, yes.
Yeah, so there are like explicit barriers between layers to make sure everything comes in. But within a layer, yes. And of course, this you could do other mappings as well across layers. And this we don't have.
Is it also hardware managed or software managed?
It is
hardware
managed. Yeah.
Yeah, kind of. Yeah, for that. Yeah, that one is hardware managed. Yeah.
Another way to think of the layer as done barrier is that you're counting the number of writes into the global buffer.
Yeah.
And when the number of writes into the global buffer equals what you expected, then you're done.
Exactly.
You don't need any other barrier before.
Yeah.
So you just have a counter.
Yeah. You'll see that feature inside the source code. So for details, so basically we have the kind of barriers for each folding, which means the when we reach one at the end of one dimension, then we need to go over to the next elements. For example, if we have input image and if we are done with the one row and we want to go to the next row, then before that we have kind of barrier on there. So before we update the switch configuration, we make sure that we receive all the outputs before we proceed. Okay. So this is the entire structure. So we have controller and pre-patch buffer, which is the global SRAM. And we have also activation units. So we can implement any kind of nonlinear function using the lookup tables. So that's the activation units. So this is about the regular data flow. So mainly about regular data flows. So basically, so if the DNN topology, which is the shape and size of layer, changes, and also if the layer type changes, then we have different style of data flow inside it because so for example of the layer shape, so if we have one layer you have an input image width of 10, and another layer if you have input image of 20, then the number of iterations is different. The frequency of the data request will be different, and so on. So that affects the buffer requirement and all the other aspects of the data flow. And we might have some loop reordering and loop tiling size and cross-layer mapping. All of these things are related to the reordering the loop nest and having more level of buffers inside it, and so on. And we even have some kind of sparse workload. So that introduced some irregularity inside CNN. So I'll talk about how MAERI deals with such cases. So our key insight about these kind of cases, yeah.
You focus on, I guess, reduction trees, but they're like TPU uses historical.
Yeah.
There's like more. I think there's more local reuse. So what do you think of the two architecture?
Yeah, the definite benefit of the TPU-like system array is the cheap hardware. So because it's simple, the flow control scheme, and it only requires only 5 bus tau the buffer, so it requires much less energy and could be much more less energy.
Also, but one way of thinking of it is even in the TPU, so it does. So I think your broader question was like, what do you think of kind of a tree-based thing versus kind of
where should we go?
Right, so that's a good question. So one way, so after thinking about it, or one way the way I view it is, so we talked about kind of these virtual neurons, right? So here in MAERI, it's like a very 1D entity where all of these multipliers are like that, and then you create these virtual neurons. So if you kind of, let's say, had fixed size virtual neurons and then made it into a 2-dimensional thing, you would essentially get something like this systolic array. So the same data here kind of is multicast to 2 entities, while in a systolic array that will essentially become like store and forward multicast, the way I had kind of talked about earlier. So here you kind of have one multicast to all the PEs that need that data, or all the multipliers. In a systolic array, they would be forwarded. So I guess like intuitive, this kind of, that's one way of viewing it. The benefits this design then has is actually what June just mentioned here, right? So neurons of different sizes. So if you, the problem in a systolic array is if you don't have weights, let's say that, if you have a weight size or a filter size that's smaller than the number of rows you have, you'll just have underutilization. While here you don't have that problem because you can basically use everything. But the cost you're paying here is in some senses, we kind of have these small switches that you attach to everybody. So while there it's just local formatting. So there's, I guess you probably had, I think we were just having that discussion yesterday.
We were. But so I want to give the NVIDIA perspective a little bit too. So the first point to note is if you have this sort of array where you say weights come in here and inputs come in here and you go choo, 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 choo. It's actually less local reuse than you might think. Almost everything is moving. Now it's moving very close to where it was, but it's still toggling the wires. Whereas if it's a true stationary data flow of saying I'm going to hold it and not move it, that actually is toggling less wires. So you get less energy there. And as June said, if you build a very big array, you end up with underutilization. The other point is if you look at what the tensor cores are in the GPU, that's essentially just a small systolic array, 4x4 or whatever it is for Volta. So essentially it's saying, can you capture the majority of that benefit with a smaller array? Draw a box around that, call that an SM. You have multiple of those. Those are working on different sub-problems. And you can sort of capture, like, I don't know what the number is. Let's say 70% of the benefit of the and with a much more larger degree of programmability, right? That's what NVIDIA is sort of doing.
Yeah.
So I wanted to ask an NVIDIA guy. So if you wanted to do like an A or the U, you have to read from the big L1 cache every time.
No.
Isn't that
So the tensor core is doing the chunk thing without going back to the.
Okay, so there's like a better.
So the whole reason you do this thing is to the surface area to the perimeter to volume ratio is favorable. So even though it's a 4x4, you only need 4 things here, 4 things here, not 16 things, and it scales up. Right. Right, but we can also talk about this during the coffee break and stuff.
Yeah. There's actually, I mean, I think just between this style versus the systolic style, we've kind of have both qualitative and quantitative things that we can talk more.
Right.
And I think it's a part of
discussion.
Do you like dot products or do you like matrix multiplies? Which is the series of dot products, right? They're like 8 of 1, half a dozen.
Yeah. Thank you for a great point. So, yeah, the granularity of the sister array is very interesting. So, I just wonder, so if we reduce the sister array size to 1 by 1, then do we get similar thing or not? So yeah, something like those things. Yeah, I'm happy to discuss that further after this tutorial. So anyway, so our key insight about this kind of all irregular data flow is they can be translated into different virtual neuron sizes. And if we can map any sizes of the virtual neurons, then we can support them efficiently. So let's take a look at some examples of the mapping. So this is dense data flow, which is normal case. So just for example purpose, I map the VN of size 5. So it doesn't happen in CNN usually, but let's take a look at this example. So I just wanted to introduce some irregularity that goes over the power of 2. So this is the mapping of the entire virtual neurons with size 5. So as you can see, you can map all the data movements as the arrow indicates. But what about the irregular cases? So this is about sparse convolutional layer. The red virtual neuron, which is VN0, has size of 5, and VN1 now has size of 6, and VN2 has size of 4. But as you can see, we can still support the entire data transfer without bottlenecking from the network on chip. So for a fully connected layer, so basically you can translate a fully connected layer to a large convolutional layer. So you can imagine the VN is very large and folded over several times. So MAERI can support these cases. So different layer type in this case. And LSTM is also very similar to the fully connected layer. So we also support the LSTM.
This also becomes actually an interesting design point versus a systolic array, where for fully connected and LSTMs, essentially you can only send them across one row. So unless you have batching, you don't get a lot of like utilization.
You wouldn't have batching.
And yeah, exactly. So that's,
you're right.
Yeah, and that's true. I think even in the TPU paper, you can kind of see that LSTMs have very low utilization over these days. So I think that's
because it's memory.
it's both actually. So when I spoke, it's a bit of both. So I think the paper, most of it is memory related. But from what I understand, the reason why the subsequent generations did not just increase the array size is because it would lead to issues like that. So it's more valuable to, I think, have smaller of those arrays, and that's as it was. He said that's what the tensor cores did as well.
Yeah. So thank you for bringing it up. So another point regarding the
you can buy a Volta, you can't buy a
Yeah.
Sorry, excuse me. I'll shut up now.
Okay, so another point regarding the sister array. So to support sparsely inside sister array, we need to insert bubbles. But with this structure, we don't need to insert any bubble and map as much as we can.
Can you go back to the
Sure. This one?
What if I have only 15 neurons instead of 16? next, the last one is kind of zero, but they do.
You mean this one?
Yeah. Suppose I don't have that.
Then yeah.
Then
For this kind of mapping, it will support.
so it's a log map tree when you do the reduction or when you do the polling. Then the number of layer of the adder.
You mean?
Sorry, you combine two. In one adder, right?
Here?
Yeah.
Oh yeah. In this case, we just ordered.
So I guess what's the question? Is it
How big of a reduction tree do you need? Is that
Yeah.
Oh yeah.
So if you tell us a very odd number the input before you go to the tree.
so the actual that's a good question. The actual number of multipliers we use are powers of 2, at least in the design, in the physical hardware, so that you can create a tree. You can map any number of things on them, but in the physical hardware you can only generate like 16, 64 to 56.
Yeah. But theoretically, so we also have proven certain features of the reduction tree, and based on that, we can support any number of
you can actually trim down and remove a few, and it would basically that last adder would not be an adder; it will just be a
exactly.
unbalanced.
Yeah, you can get unbalanced.
Right. Okay. So we have much more details inside our paper. So if you are interested in, please refer to our paper. And let's visit the source code and MAERI front end. So source code directory structure you will see inside VM will be something like this. So actually the directory name has changed. So MAERI code ISCA 2018 tutorial is just MAERI. And you will have script directory and source directory. And source directory will have this kind of subdirectories, but the directories marked with red color is the core implementation of the MAERI. And let's talk about how to use the MAERI frontend. So to change the configuration, so in the top directory of the MAERI, so you will see a file named as the accelerator config. So by modifying numbers inside the file, so you can easily modify the configuration such as the distribution and reduction bandwidth and number of the multiplier switches. And to generate the Verilog and to compile the simulation, you can use these kind of commands. The C is compiling the simulation and R is launching the simulation and so on, but I'll visit all of this while I'm doing this demo. So if you run simulation, so which is cycle accurate simulation, you will see some results like this. So it will give you the input the layer dimensions, and give you the counts of the injected weights and inputs, and counts of generate partial sums, and give you the number of performed max, and the most important thing is total runtime in cycles. So using this information, you can easily calculate the gigaflops or teraflops of the given architecture. And for verification purpose, you can compute the exact number of the input and weight injection counts and number of partial sum generated and compare it against it, which will be the part of the exercises. And it also generates the VCD file, so you can load it to any waveform analysis tool. So if you are a Verilog guy or VHDL guy, then you will be familiar with this one. And you can generate Verilog using the configuration by typing -v option, and it will be generated under the Verilog directory under top directory. So I'll do all of this thing in the demo again. And please note that the generated Verilog is fully synthesizable. So for example, so for a proof of concept, so we synthesized it and did PNR of the generated Verilog using this environment. So technology was the TSMC 28 nanometer and 1 gigahertz clock frequency and 64 multiplier switches, which can be also thought as the 64 PEs, and various distribution and gather bandwidth. and RTL code is generated by the BS. Yeah.
So for this bandwidth number that you have, for 64 multipliers, when you say 16, you only supply 16 unique numbers?
Yeah, so, yeah, right, yeah. So you can modify the parameter if you need more, but this is just for some kind of the predefined settings to synthesize the design.
You need 4 cycles one by one.
If you need to deliver the data which are all different, then yes, right. But usually, so we have implemented multicasting inside this. So our inside is we usually don't need that amount of bandwidth. So by network concept design, we are exploring the spatial data reuse. So we synthesize all the generate code using this kind of CAD toolchain, so Synosys Design Compiler, Cadence Innovus, and uses prime power to get the power number. So this is a brief result. So I just put one of the generated layout here, but you can see the area and power generated by the CAD tools. So this is post layout number.
And I think another interesting thing is you can kind of see how the distribution and the reduction bandwidth kind of affect your total area and power, and that's kind of that whole design space exploration to see, given your target area and power budget, like how much you would want to.
Exactly. Yeah.
So if as I think, or following on Nachiket's point, right? So if you provide like 64x bandwidth, 64x reduction bandwidth, you can basically deliver a new piece of data to every multiplier every cycle and collect a new output every cycle. But that is kind of the extreme version where again there's probably no reuse happening, which is not going to be that common a case. So you can again kind of tune. While if you just have 1x, then it might be too low of a. So that's kind of where we kind of see, like, Maestro and MAERI kind of coming together, where Maestro gives you kind of some insights on which data flows and like what is the kind of reuse you get, and then you can generate RTL and get some area power.
Yeah.
One more quick question.
Sure.
Right, on the previous slide,
Mm-hmm.
you said there are 31 adders. 31.
It should be 63. Right?
No, so we only need a 31. So I'll come to that point. So yeah, that's an interesting point. So actually, that was part of an optimization. So for adders, so for the lowest level, we don't have separate adders for here.
Oh yeah. Okay,
So by that we reduce one level.
Okay.
So
That I understand.
Yeah.
But you have the fatness of the upper things, right? So
Right.
the question is, you still just have one adder in the upper stages, or do you have as many adders as the number of?
Just one adder is enough to support any mapping. So
Yeah.
that
So
requires
actually, good point.
serialization, right? That would mean a serialization. Like, even if you had multiple links feeding the adder,
Yeah.
you only do one adder.
one adder, yeah. So we've seen that for a variety of mappings.
So actually,
yeah.
so to answer actually your point, right, Nachiket? So the idea is that you don't need, so the fatness is just required in the links, like the adders at the top level just actually act as forwarding paths, because so the actual output activation is generated at one of the adders at one of the levels. You don't need, so if you needed 2 adders at the topmost level, that basically means that you have, that's not possible because across the multipliers, that means 2 things are simultaneously getting reduced, right? So you anyway have only, so if you map one entity across all the 64, then you would just have the topmost adder generating the final sum. If I did the other extreme where I just have a virtual neuron size of 2, then all the adders at the first level would generate the outputs, and then you just need forwarding. So yeah, so the number of adders is just 31, but the number of wires is actually...
Yes, right. Yeah, intuitively, the minimum number of adders to support the worst case will be that, the given number, and we achieve that by providing reconfigurable links. Yeah. Okay, so this is about the synthesis result. So as you can see, the generate value is fully synthesizable. And let me do some demo. So let's move on to the MAERI directory at this time.
So again, same question. Like if if for those of you who already downloaded it, yeah, you can basically go to the MAERI directory.
Yeah.
If some new people arrive, we have pen drives here if you wanted to launch it.
Yeah. Please let us know. Yeah. So in the to begin with the very start point, so we will have.
Pass this around, so we just wanted to get a sense of the number of attendees. So if you could sign in your names in case you haven't.
Yeah. So we have ISCA 2018 when you open the terminal. Then under the ISCA 2018, you will see the MAERI and Maestro. And this time we will go into the MAERI part. And this is files we have here. So the executable, the MAERI, is the script that launches all the functionalities regarding the source code base. So if you just type MAERI, then you see which option is available, like here. So I have pre-compiled the simulation. So let's simply launch one of the simulations, then see what happens. So
you can see that why you want analytic modeling for running whole layers and stuff.
Right. So actually, this is a very small layer, just for the example purpose. So you can see the layer dimensions like here. So K is 6, and C is 6, R and S are 3, and Y and X are just 5. So it's toy size. But what about larger layers? So we have pre-compiled simulations here, and what about we have 64 multiplier switches and late layers, which is we have some kind of synthetic late layer. So I'll show you the dimension of it soon. So if you run this layer, as you can see, it requires much more time.
And this is still just a synthetic layer, right?
Yeah,
not VGG.
It is pretty small. So I'll show you the actual dimensions. So under the accelerator config file, so you can see many parameters. So let me visit one by one. So at the top level, so there are user configurable parameters such as the distribution bandwidth and the reduction bandwidth. And you can also specify number of multiplier switches, which can be translated to the number of PEs of the accelerator.
And if you change any of those, you'll have to recompile.
Right.
Those are static parameters.
Yes. And in this test bench, we only support 32 and 64 multiplier switches, but that's because it requires the switch configuration pre-generated. So, but we only added these two cases here. And so we provided several layer dimensions. So you can run VGG convolution layer first one, and which is early layer, and VGG convolution layer 11, which is late layer. And because they are too large, so we also provide the synthetic layers, which has similar characteristic of the early layer and late layer of other convolution layers. So early layer has larger input dimensions, but smaller number of the input and output channels. But for late layers, it has more number of input and output channels, but small dimension of the input image. So the simulation I launched just before is the late synthetic one. So as you can see, this is still pretty small, but it takes a few minutes to.
And it'll be running on your laptop, so a faster laptop will go faster.
Right. That's also true. Yeah. But basically, it is cycle accurate simulation, so it requires some time. So that's why we need Maestro. So anyway. And if you want to launch new simulation, and if you want to compile a new one, then you can just type C, then it will compile a new simulation. So if you just type C, then it will compile with a very small toy layer, which is defined here. So K and C are 6, and Y and X are just 5, very small one.
So quick, just so that
Yep.
people are clear. So the simulation, so when you recompile, so the first part where you specify the parameters, right, number of multipliers and so on, that's
Yes.
the one that, as we said, like that is the one that decides what the accelerator configuration
Exactly.
is.
Yeah.
These layers are just kind of related to
Test bench.
the
Yeah.
test benches,
Yeah.
right? So the reason for recompiling in some sense is the test bench then creates the configurations for the switches. Right?
Yes.
So that's the only reason. Like the actual hardware cost will be the same, whatever. I mean, like if you actually generated Verilog, it would be the same. It will only depend on the top.
Yeah.
It's saying that if you had a compiler toolchain, you wouldn't have to
Yes,
do
exactly.
this.
So the
Exactly,
thing that's missing is we don't have a compiler toolchain for MAERI which would automatically map them. So we kind of have separate test benches, which each of them just creates a separate mapping for each of them. So
Yes.
So on that note, which is why when you said that right now we support 64 and 256,
Right.
So if you wanted 256 multipliers,
Right.
you would just need
Generate
to
some
add,
new configuration.
So where would
looks
that
like
be
this.
if somebody wanted to do that in the code?
Where does the configuration files live?
Oh, it is embedded into test bench.
Okay.
Yeah.
So if exactly, so that's that if condition. If value of num
Yes.
which is equal to 64, that's so one can basically kind of create another version with 256, and yeah, we're working on a script that will just do this automatically.
Yeah, we are currently working on this one, so hopefully we can release it.
Yeah,
Yeah.
soon. But this code is out there. We can.
Yeah.
One question. The test bench is automatically generated based on the accelerator file.
So test bench automatically generates the schedule of the data communication. Yeah, so based on this configuration, and it generates the inputs to the MAERI accelerator. So at certain time we need to send weights to which destination, and at next we need to send inputs to which multipliers, and do we need to multicast it or not? They are automatic.
Yeah. So all of that is automatic. The only thing that's put in right now is the config. So we talked about kind of virtual neurons, right? You have to configure the switches so that the adder knows whether to just forward or add. So that's something that is currently like statically configured in the test bench.
Yeah.
And then we need a reference model, right? Because how do you know that your design works correctly? You should have some reference.
Yeah.
So how do you know when?
Yeah. So I'll show you that.
Yes. So yeah, that's something.
Yeah. So to show that, let me just compile the smallest one. Yeah. So it'll take some time, but anyway. So basically what you are doing is after the simulation, we see the input and weight injection counts and number of partitions generated, and we can compare this number to the expected numbers. So I'll show you. Yeah.
Or you can look at the waveform.
Yeah, sure. So after this one, so if you run this thing, and the number of injected weights and inputs, those are based on the simulation. So simulate the statistics registers inside the test bench, and let's compute what is the exact expected numbers. So for weights, the four dimensions, the K and C and R and S, they are related, and basically the number of total weights is the multiplication of all of those dimensions, right? Yeah. So K is 6 here, and C is 6 here, and R is 3, and S is 3. Then you'll see this number matches the injected number of weights. So we can do similar things for each statistics.
We can probably add an initial thing in the beginning because the inputs are, and just say these are the expected numbers, and this is what was actually observed.
Yeah.
So that then, yeah, people will know if something actually
Great.
went.
Yeah, that's a great point. Yeah.
So we can just do that actually in the.
Yes.
We'll put that as a.
Yeah. So yeah, for
that's actually how we have debugged the code in the past. Like if we saw that there was some value that never reached, so we know something went wrong.
Yeah, exactly. So yeah, this is how we launch simulation and see how it goes. And if you launch the simulation, then the VCD file is automatically generated. So if you type MAERI-W, then it will automatically launch GTK wave and load the dumped file, and you can see some kind of clock is always there, and I'll show you this one.
Correct. Do we end up giving them a pre-made file to look at?
Oh, I have that. Yeah, sure. There's a pre-generated file. So GTK wave. So this is for larger layer, so which could be more interesting. and read C file. So I just placed some counters for counting the number of iterations over each dimension. And I didn't mention it yet, but the data flow of the test bench is something like this. So the data flow of our test bench is something like this. So we have C at the top level, and K and Y. And yeah, K is spatially mapped actually. And R and S are on road, so they are actually kind of spatial mapping by combined with the tile pragma. So because K and R and S are all related to the weights, so it has high weight filter parallelism inside it. So this is our data flow. So in the waveform, what I did is I added a counter for the iteration for each variable, so C and K and Y and X. So counter C and K and Y and X. Yeah, because C was at the top level, so it changes more, the most slowest frequency, and K is faster than C but slower than Y and X, and next one is Y and next one is X. And you will see some irregular patterns around here, but it's because of the folding. So if we have 16 multiplier switches, and if we want to map kind of some 20 inputs, something like that, then we have some small remainders at the end of the iteration.
In the first iteration,
yeah.
do 16, next iteration you just do 4.
Yeah.
And you have 12 that are unused. So you could, in principle, use those 12 for other things. That's where you will need a compiler to kind of do that. That's something we don't
exactly.
have yet.
So this would be input channel stationary.
Yes, right. Yeah. And each virtual neuron maps the output, one output channel spatially. So we can also do this, and finally we can also generate value just typing MAERI-V. So it also takes some time, but basically it generates a value file under the value directory of under MAERI. Yeah, this is VM and on a laptop, so it takes some time, but anyway.
It's VM on a laptop, but I guess even for me it's impressive, right? So now basically we are just generating the RTL for an accelerator, right, on our laptop, right, which is pretty neat.
Oh yeah.
Yeah. So
right. And you can configure the structure by giving the parameters, so, which is great.
And of course, one thing you can do is for an even, of course, one could take the Verilog and send it and do an ASIC flow, but you can also put it on an FPGA. So we actually, I don't think in the presentation we put, but we also put it on an FPGA and got some results. Right? So it kind of both does a validation, also gives us some estimate of how much it's taking.
Yeah.
What clock frequencies do you typically get on an FPGA?
I need to check actually. I don't know if you're sure what
I didn't have that information from yours.
The clock frequency was pretty
the
good.
ASIC was gigahertz.
Yeah,
but on the FPGA,
it's interesting whether it's double digit or triple
I am
digit.
actually
Right. That's an impressive point.
Yeah. So one of the undergrads in our lab actually just sent us some results last night, but I don't think he told us what the frequency was. But I can get back.
I wouldn't be surprised if it's around 100.
Yeah. So in fact, one of the things that we're trying to now do is actually Nachikeet just left the room, but he's an FPGA expert. So we're trying to kind of make the code more FPGA friendly, because if you think about it, the switches are really tiny. So we can kind of, if you can probably map them very efficiently.
Yeah.
If you, I mean, right now, of course, this is just push button Vivados. It's not doing any optimization. But if you did that, you could actually get it to be much lower.
Yeah, okay, so this is the generate value code, and so unlike some other value code generators, it preserves the signal names here, so which is much readable. So I believe this will be useful for integration.
just do what L in your shell. Just do to get the line numbers of Verilog.
Oh,
there. So
let me recall.
Ln-S. What is it? no, that's the link.
No, that's
What is it?
no, I don't think
It's
it's
WC, right.
WC.
Oh, the word count.
Makes much more sense. WC-L.
Yeah.
Start RT.
Wrong,
Yeah,
wrong.
45,000 lines of error.
Yeah.
Most
For
of which are in the distribution tree and the reduction tree.
yeah,
Which makes perfect sense.
yeah, that's the core implementation.
Yeah.
Okay, so this is the end of my demo, and let's.
So actually, I'll just ask because Nachikeet is back. So do you? We were just trying to understand how much, if we put this on an FPGA, what would the clock frequency be? And so I don't have those numbers directly, but just intuitively, like for the trees that you have put up in your lab, what frequencies do you guys usually get?
400
Megahertz. Okay,
That's pretty good.
actually
That's pretty good.
But of course, that's code that's FPGA optimized. This one is not. So I'm actually very curious how far this is from.
Also, the MAERI I have doesn't have address.
Okay, yeah.
How many bits do you have? 30?
The data is 16-bit, and I need to double check the metadata.
But the accumulator stroke can be bigger than the data.
Yeah, right.
We'll talk about that later.
Yeah. Okay, so this is how the code base work.